A very good morning to everyone. This is Dr. HimaBindhu, Assistant Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering. And today we'll be learning about the rotational matrix. What is the use of a rotational matrix? What is the purpose of the rotational matrix? Why is the rotational matrix is actually being used in robotics subject? Why it has been introduced in robotics? The purpose of the rotational matrix in robotics we will be learning. Right? What do we mean by rotational matrix actually? Right? Coming on to the rotational matrix, what do you mean by rotational matrix actually? Yes, the rotational matrix is nothing but it is used to represent. The rotational matrix is used to represent the orientation. The rotational matrix is used to represent the orientation of the robot arm. Right? Rotational matrix is nothing but it is used to represent the orientation of robotic arm. That is how a robotic arm, where is the position of the robotic arm? What is the position of the robotic arm will be represented by a rotational matrix. Till now, in all the previous sessions, we have seen about the movement of the rotational matrix, how the movement of the arm is being done, or how the movement of the end effector will be done, using like using actuators or using any particular type of sensors, how this particular arm and the manipulators were being working, we have seen. But what is the actual position and how is the actual position or how is the actual orientation of a robot being calculated, that we have not seen. So generally, a rotational matrix is used to represent the orientation of the robotic arm mathematically. Right? The orientation or the position of the robotic arm is being represented mathematically in the form of matrix. Right? In the form of matrix, we will be representing the position of the robotic arm. So, generally, this particular matrix will be given in a 3x3 matrix. Why are we taking 3x3 matrix? Yes, generally the rotational matrix will be represented by a 3x3 matrix. Why are we taking 3x3 matrix? What is the consideration of 3x3 matrix? That is, here we will be taking 3 coordinates. Right? The 3x3 matrix will be represented because we will be considering 3 coordinates. Now, these particular 3 coordinates are nothing but x, y, and z coordinates. The rotational matrix will be represented by a 3x3 matrix. The 3x3 matrix will be considered because the position or the orientation of the robot will be done in 3 different coordinates, right, on 3 different axes. So that particular 3 different axes is nothing but we consider x, y, and z axis, right, where this particular axis will be rotating at an angle theta, right, where this particular axis will be rotating at an angle theta. Now let us see this particular figure. Now, what do we understand by this figure? Right, here we can see x-axis, right? Here we can see an x-axis. Here we can see a y-axis, and we can see a z-axis. Right? Here we are considering 3 axes: x-axis, y-axis, and a z-axis. Right? Now, these particular axes are initially rigid. Right? these particular three axes are initially at a rigid position, right? The axis which we are considering, x, y and z axis, these particular three axes, x0, y0 and z0, we are considering are being placed at a rigid position. Now, when we are considering a vector, P, it is also fixed, right? When we are considering a vector P, this particular vector P is also fixed, where it depends upon the movement, it depends upon the rotation of the axes, that is x0, y0 and z0, right? The vector P is also fixed to the axis x, y and z, where the movement of the vector P will be depending upon the rotation of the rigid axis x, y, z in terms of x1, y1 and z1, right? In terms of x1, y1 and z1, in terms of the rotation of the axis of x1, y1, z1, the fixed vector P is also rotating simultaneously with the axes x1, y1 and z1. Now here we can see when the rigid axis x0 is being rotated, it is rotating at an angle theta, where it is moving at some distance, where we consider that particular axis as x1, right? Whereas when we are considering the y-axis is also rotating at an angle theta, where it is moving to a position of y1. And the z-axis is also moving perpendicular to z0. The z-axis is also moving perpendicular to the z0, where it is being given as z1, right? This z-axis is moving perpendicular to z0, where it is being represented as z1, and this fixed vector P is rotating along the side of x1, y1 and z1 at an angle theta, right? At an angle theta. So this is how the rotational matrix will be done for a three-dimensional plane, right? When we are considering a three-dimensional plane, this is how the rotational matrix will be calculated. Now, when we take a two-dimensional plane, right? When we are considering a two-dimensional plane, here we will be having an x-axis and we will be having a y-axis, right? When we are considering a two-dimensional plane, we will be having an x-axis and we will be having a y-axis, where z0 and z1 will be at some origin, right? Whereas the z-axis has been placed at the origin. Now, here we have the vector P is being taken, where it is being fixed, and the movement of that particular vector will be done with the help of the rotation of the x and the y-axis. The movement of the vector P for the frame will be done with respect to the movement of the frame, that is, or movement of the axis x0 and y0. When the x0 is been rotating at some angle, right? When the x0 is been rotating at some angle, it represents the x1 axis. When x0 is been rotating at some angle, it represents the x1 axis, and when y0 is being moved or rotated at some particular angle, it is representing the axis y1. Now, how is this particular vector P be denoted then? Right? So, when we are considering, when we are drawing a perpendicular to this particular vector P, now from point P, when we are dropping that particular point P onto the x-axis, it gives us the representation of px0, and this particular path is being considered as px1, right? When we are dropping the vector P onto the y-axis, it gives us the representation of px0 on the x0 axis and px1 on the x1 axis, right? When we are drawing a perpendicular line for the vector P onto the x naught, it gives a vector px0, and when we are drawing a perpendicular line onto the x1 axis, it gives a vector px1. In the same way, when we are considering for the y-axis and we are drawing a perpendicular line from the point P onto y1 axis, it gives us a vector py1, and when we are dropping the particular vector, this path, right, when we are dropping the vector onto py1, this particular path is called as py0, which we have represented here, right, which we have represented here. Now this particular axis is being called as py0. Clear? When we are considering a two-dimensional plane, for that particular two-dimensional plane, we will be having only two axes, x and y. Now we have x0 and y0 axis, which we have considered, and z0 and z1 are in the origin. Right, in the origin, and by the movement of the x0 axis with some particular angle, we will be getting an axis x1, for which a vector, when we draw a perpendicular vector, we get a p1 axis, and when we are rotating the y0 axis at some angle, we will be getting an axis y1. When we are dropping the perpendicular vector p onto the y1, we get the axis py1. In the same way for py0 and px1. So this is how we represent it for a two-dimensional matrix. Now for this particular two-dimensional matrix, how do we write the rotational matrix? How do we consider, or how do we write the rotational matrix? Now, for a two-dimensional matrix, we write the rotational matrix as px0, y0 or px1, y1 for the vector, for the frame 1 or for the frame 0. Right? For the frame 1, we write the vector as p superfix 1, which is equal to px1, py1. This is considered for a two-dimensional figure. And when we are considering the frame 0, the superfix of the vector p is equal to px0 or py0. The same when we are considering it for a three-dimensional figure. This is for a two-dimension. When we are considering it for a three-dimensional plane, we get the vector as px1, py1 and pz1. And this in the form of px0, py0 and pz0. Right? So this is how we write the vector representation. That is, the vector p is fixed to the coordinate system x1, y1 and z1, as I have told you in the earlier one. The vector p is being fixed to the coordinate system x1, y1 and z1, and the vector p rotates together with x1, y1 and z1, which is giving us the projection, in px1, y1 formula, that is in the form of the matrix. That is, the coordinates of the vector p is given by its projection frame 1. For that is, when we are considering the projection for frame 1, it has been given as px1, py1, pz1. When we are considering the projection for frame 0, it has been given as px0, py0 or pz0, depending upon the type of the plane we are considering. If we are considering two-dimensional plane, we will be getting two projections. If we are considering a three-dimensional plane, we will be getting a three projection in this particular form. Right? We will be getting a three-dimensional matrix in this particular form. That is, here in the rotational matrix, actually, we are searching for a matrix that can transform the representation from the coordinate system 1 to 0. Clear? Here in the rotational matrix, we are generally searching for a matrix which gives us the transformation from the coordinate systems 1 to 0. So when we need to transfer the representation of the coordinates from 1 to 0, we write that particular matrix equation as P of frame 0 is equal to R1 to 0 into P of frame 1. That is, vector projection of frame 0 is equal to the representation or the transformation of the coordinates from frame 1 to frame 0. Right? The transformation of the coordinates from frame 1. This is frame 1 to frame 0 we are transforming, and that is being denoted by a letter R, and this into the projection of frame P, frame 1, the projection of the rotational matrix of frame 1, right? So this is how we write the transformation matrix for representing any particular coordinate system. In order to transfer the representation from frame 1 to 0, we write the particular equation in this particular form. That is, the projection of frame 0 is equal to the representation from the transformation of the coordinates from frame 1 to frame 0 into the projection of the frame 1. As I've told you, always a rotational matrix is a 3 by 3 matrix. Right? Always, as I've told you in the earlier, the rotational matrix is always a 3 by 3 matrix which gives a rotation at an angle theta. Right? Which gives the rotation of the axis at an angle of theta. Clear? So when we consider the unit vectors for the same projection lines, right? When we are considering the unit vectors for the frame 3-dimensional plane, right? Now, as we know, this is the axis y0, this is the axis x0, and this is the axis z0, right? Now, this has been rotating with some angle theta, where the axis y0 is rotating with some angle theta to the axis y1, which gives a unit vector of ji, right? Which gives a unit vector of ji, and this z0, as I've told you, is always perpendicular to each other. So it is perpendicular, the z0 is always perpendicular. So we are getting the axis z1 on the same axis of z0, which gives a unit vector of k1, right? Which is giving a unit vector of k1, whereas the x-axis x0 rotating at some particular angle where the axis has been rotated to x1 plane, giving us a unit vector i1 as well as a unit vector i0, and here also we are getting a unit vector j0. So here what we are having, what are the unit vectors we have? I0, J0, K0, and I1, J1, K1, right? I0, J0, K1 are the unit vectors for the coordinates x0, y0, and z0, and I1, J1, K1 are the unit vectors for the coordinates x1, y1, and z1, right? Previously we have seen the vector p. Now we are considering, when we are considering the unit vectors, right? This is the vector, fixed vector which is being fixed. And now when we are considering the unit vectors for the same rotational matrix, we will be getting I0, J0, and K0, which are being determined on the coordinates x0, y0, and z0. Similarly, the unit vectors I1, J1, and K1 are the unit vectors which are being represented on the coordinates x1, y1, and z1. Clear? Now, when we are considering that particular unit vectors, the representation of the vector p for the frame xyz, the representation of the vector p for the frame x, y, and z is being written as the vector p at frame 1, the vector p at frame 1 is equal to the vector px1 into unit vector I1 plus py1 into unit vector j1 plus pz1 into unit vector k1. Right? This is for x. This particular thing is for x1, y1, and z1 projection. When we are this projection of frame 1 is been represented for the projections x1, y1 and z1. And when we consider the vector projections for x0, y0 and z0, we give the representation of the vector as projection, the vector p at frame 0 is equal to px0 into I0 plus py0 into j0 plus pz0 into k0. Right, this is k0, z0 into k0, which is considered as equation 1. So here we have got two equations with respect to the vectors p in terms of the projections x1, y1, z1 and in terms of the projections x0, y0 and z0. We have got two equations which are representing the vectors at frame 0 and vector at frame 1. Now, from these particular two equations, from equation 1 and 2, we can write the projections for x0, we can write the projections for y0 and we can write the projections for z0. How we write these particular projections? It has been written in terms of frame 1. When we are considering frame 1, in terms of frame 1, we are writing projection of frame 1 into I0 or projection of frame 1 into J0 or projection of frame 1 into K0. That is, we are considering one particular column. So here we write the equation as Px1 into I1 into I0 plus Py1 into J1 into I0. That is, here I0 is common. Right, here J0 is common and here K0 is common. That is these particular terms. Right, with respect to these particular terms, we are multiplying the projection axis. Right, with respect to the common terms I0, J0 and K0 unit vectors, we are multiplying the projections. So here Px1, I1 into I0 plus Py1, J1 into I0 plus Pz1, K1 into I0. This is one equation for Px0. When we are considering the Py0, Px1, I1 into J0 plus Py1, J1 into J0 plus Pz1, K1 into J0 is the second equation which we are getting for the unit vector J1. Now thirdly, for the unit vector k0, we get the equation as px1 I1 k0 plus py1 j1 k0 plus pz1 k1 k0, which we consider it as equation 3. So here we have got the equations for the unit vector x0, y0 and j0. When this particular unit vectors equations are written in terms of matrix, rotational matrices, how do we see? How do we consider? So here we are considering the unit vectors px0, y0, z0 is equal to the equation, projection equation I1, I0. This is for the column 1, I1, J0, I1, K0. That is, for the column 1, we are considering the vector x0. For the column 2, we are considering the vector J0. And for the column 3, we are considering the vector z into the frame 1 axis. Into the frame 1 axis, that is px1, py1 into pz1. Right? The frame 0 axis, the projection of the frame 0 is equal to the representation of the projection from frame 1 to 0, right? The projection of the x-axis in terms of x0, y0, z0 is equal to the representation of the projection in terms of frame 1 to frame 0 into projection of the axis in terms of x1, y1 and z1. So here representation of the projection from frame 1 to 0 is considered as column 1, 2 and 3. Here we have a 3 by 3 matrix. So this particular 3 by 3 matrix is written as in terms of x0, y0 and j0, and in terms of x1, y1 and z1. So this particular term is called as is for the projection P naught, right? And this particular matrix is for the projection P1, and this particular matrix is known as 1 to 0, the representation 1 to 0. That is, projection P is equal to the representation of the projection from frame 1 to 0 into the projection unit vector, the projection of the vector for frame 1. Right? So the above is the rotational matrix. The above whatever we have written is the rotational matrix which represent the transformation from frame 1 to frame 0. Now, as I have told you, we have discussed about the first column, second column and the third column in the previous diagram itself. This is the first column, second column and the third column. So, that also how it is being represented, I have told you. That is, the first column will represent the projection of the vector I1 on the axis of the frame x0, y0 and z0, as I have told you. Right? That is, the first column will represent the projection of the vector I1 onto the axis of the frame x0, y0 and z0. And the second column represents the projection of the vector J1 onto the axis x0, y0 and z0. And the third column represents the projection of the vector K in terms of x0, y0 and z0. Clear? Now, since here I0 and I1 and I0 are unit vectors, right? Since I1 and I0 are unit vectors, this particular I0 and I1, when we are calculating, what we are getting? The unit vectors, when we calculate according to the graph given, what are we getting? That can be represented by this particular figure, right? So, when we are considering this particular plane, it is nothing but cos, right? When we are considering this particular plane, it is nothing but cos theta. But when we are considering this particular plane, it is nothing but sin theta. Now, when we are considering here, which is coming outer, so this will become minus sin theta, and this angle is nothing but the cos theta. Clear? This is nothing but the cos theta when we are considering this particular graph. So, accordingly, what is I1 and I0? It is nothing but 1 and 1. We don't have any values. So, then we are considering the unit. Since it is a unit vector, we have the values as 1 and 1. So, 1 for I1 and I0, when we are considering, this is I0 and this is I1, right? So, when we are considering I1 and I0, the angle which we have got is nothing but cos theta. So, I1 into I0 into the cos theta. What are we getting? It is nothing but cos theta. So, that is represented here, right? That is being represented here. Now, when we are considering the next one in the same way, we will be getting sin theta. And for z, since it is a two-dimensional plane, z will be equal to 0, right? Z0 will be equal to 0. In the same way, when we are considering for the next vector, that is J1, this is for I1, and this is for J1, and this is for K1, right? So, column 3 is for K1. So, when we are considering the calculation for the unit vector J1, we will be getting minus sin theta, cos theta and 0. When we are considering the unit vector for K1, we will be getting 0, 0 and 1. This is how the rotational matrix is being written as per this particular diagram. Right? As per this particular diagram, this is how the rotational matrix will be written. Right? So, the rotational matrix is being represented from frame 1 to 0 as cos theta minus sin theta and 0, and coming to the row 2, sin theta, cos theta and 0. Coming to the row 3, it is 0, 0 and 1. With respect to the unit vectors, I1, J1 and K1. Clear? So, here the rotational matrix generally follow some particular property. The rotational matrix generally follow some particular property. So that particular property is nothing but it should follow the rotational matrix of a reversible matrix, that is a reversible rotational matrix, right? A reversible rotational matrix from frame 1 to 0 should always be equal to the transverse of the rotational matrix 1 to 0, right? The reversible rotational matrix from frame 1 to 0 should always be equal to the transverse of the rotational matrix 1 to 0. That is the property which a rotational matrix will be following, right? So, this is the actual thing which we need to consider, right? This is the actual thing which we need to prove. So, how is that being proved? The inverse of the rotational matrix is actually a transformation from the frame 0 to 1, as I've told you, right? That is, the inverse of the matrix is actually the transformation of the frame from 0 to 1. Here, initially we have transferred the frame, the rotational matrix from 1 to 0. So, inverse will be nothing but 0 to 1. So, to see this, multiply the equation with this particular term, right? To see that, we need to multiply it with this particular term. Therefore, we will be getting the rotational matrix for frame 1 to 0 for a inverse matrix will always be equal to R1 to 0. Clear? This is how we determine the rotational matrix, right? This is how we determine a rotational matrix. So, what are the properties to be considered for any particular rotational matrix to be formed? To form any particular rotational matrix, what are the properties to be considered that we have to see? That is, firstly, the column vector of the rotational matrix from the frame 1 to 0 should be normal to each other. Right, the columns of the vectors for the rotational matrix transferring from frame 1 to 0 should be normal to each other, and the length of the column vector should always be equal to 1, right? And the length of the particular column vector of the rotational matrix should be always be equal to 1. Not only that, a rotational matrix is a non-minimal description. It is a rigid body orientation. As I've told you in the first diagram, right? When we are considering a 3-axis, that is X, Y and Z axis, when we are considering, all these particular 3 axes were a rigid body axis, right? So, this particular rigid body orientation should be non-minimal description. That is, a rotational matrix is a non-minimal description of a rigid body orientation, right? And the particular rotational matrix, it uses 9 numbers to represent the orientation instead of just 3 numbers. Instead of 3, we are using 9 numbers. That is nothing but a 3 by 3 matrix, right? We are using a 1, 2, 3, 4, 5, 6, 7, 8, 9. We are using a 3 by 3 matrix. That is, total 9 numbers are being used to represent the orientation instead of just 3 numbers, right? Corresponding to the 6 relation between the 9 matrix element. Hence, only 3 of them are independent, and the orientation, the orthonormal of the rotation matrix is always representing that the rotation matrix for any particular vector which represents from the frame 1 to 0 should always be equal to the inverse of the rotation or the transverse of the rotation, right? The rotation matrix from the frame 1 to 0 should always be equal to the inverse of the rotation matrix or should always be equal to the transverse of the rotational matrix. Clear? Hope you have understood in detail about the rotational matrix. Generally, a rotational matrix is used to represent the orientation, or we also can tell it as position of any particular robotic arm. So since on all the previous classes we have theoretically dealt how a manipulator or how the working of the arm is being done, but when we need to calculate the position or orientation of that particular arm or the manipulator or the end effectors, we need to go for a mathematical calculation. So that particular mathematical representation is being done with the help of the matrices. Clear? So that particular mathematical calculation of the movement of the arm or manipulator of the end effectors will be done with the help of the mathematical calculation, which is called as matrix. So the rotational matrix is generalizedly used to represent the position of the particular robot's arm. Right, and this particular matrix will always be in a 3 by 3 matrix, and always it is being represented in a square box rather than a circular, rather than a curved shape matrix. Right, always the 3 by 3 matrix is being represented in it is a square 3 by 3 matrix. Clear? Hope you have understood about the rotational matrix in detail. Right. So this is all for today's class. And in the next class, we will be dealing about the Jacobian and homogeneous transformations and the remaining concepts of the mathematical calculations which are being used in the robotics subject. Right? Signing off for today, Dr. G. HimaBindhu. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.